ready? Are you guys able to hear me? Okay, good. Thank you. Do you have any questions for me? I posted the first assignment on Moodle. Are you able to access Moodle from there? If you have not tried it, I think I added all 4 of you into the Moodle course, so you should be able to log in. And if there are any problems, send me an email. Good. How much is the first assignment worth? All the assignments, I'm not sure how many I will have, maybe 5 or 6. All of them put together will be worth 25% of the whole course. And the remaining 75% will be split as follows. 25% for a final oral exam, no more than 30 minutes each student. And it will be a one-on-one exam. And then 50% for the projects. So that will be split as, I guess, 25% for the actual doing of the project and the report, and 25% for the presentation. That's how I've broken it down. It is on the course outline document you find on Moodle. Any other questions? How can you submit it on Moodle? Okay. Let me start the Moodle page and then show you. And I think this applies to all of you here as well. How do you submit your assignments on Moodle?
Use it.
There is a link I have set up just below the assignment. So go to the course and go down and online. Oh, okay. I guess I haven't set up the link yet. I will set it up today. I thought I set it up last night. It's very late. So you will find a link right below that for submissions. So when you click that, it will ask you to upload a single file and then submit. And I think once you submit it, that's the final. So make sure that you've done everything before you hit the submit button. And I will set it up today sometime, and then if you're still not able to see it, send me an email. And I will walk you through the process maybe over the weekend or so.
They can't see.
You cannot see the screen. The screen, you will be seeing what I'm using currently on my screen. I'm sharing the entire desktop, so that means if I'm switching from one application to another application, you will also see that. Right now I'm switching back to the whiteboard. Are you able to see it now? I'm going to switch it back to see what you guys are typing. So I'm going to switch between the Adobe Connect screen, which allows us to interact, and then the whiteboard. So how many of you are not able to see the white screen? If there is a problem, one of the things maybe your browser doesn't support it. Try Firefox, because I had a problem on my side and I contacted the help desk here, and they said that Firefox is the one that works. I'm not sure what you guys mean by saying I cannot see as well. When I'm writing, are you able to see the last few lectures? Is it happening only now? This is the white screen, okay? And this is one that you go up and down. Are you seeing it move up and down? And I'm going to switch back to the Adobe Connect to look at your response. Slide. How do you mean by the slide? Oh,
Yeah.
I see.
Okay.
My apologies. Somehow it got out of sharing the screen. I need to pay attention to many things, I guess. Okay. Now is it better?
Yeah.
Thank you. Thank you. All right. All right. Let's then get started. So we are still kind of reviewing linear algebra. When I say review, some of the things you might have seen, some of the things you may not have seen in exactly this format, but just to expose you to these ideas, and we will build on these ideas. It's a building block. Linear algebra is a building block for nonlinear algebraic equations and then differential equations. So in the last lecture, we saw what is pivoting, what is the need for pivoting. Division by 0 on the diagonal gives rise to round-off errors that are propagated. And then we saw the specific version of the Gaussian elimination, and I think I should probably do this, right? Because when I'm talking, I'll try to put a line so that people on the other side can see. Okay, Thomas algorithm for tridiagonal systems, which is a special implementation of Gaussian elimination. And then we saw the relation between Gaussian elimination and LU factorization. Basically, LU factorization collects all the processes that are used in forward elimination in L and back substitution in U. And we will see today why that is an example of why that is an extremely efficient approach. And we actually developed an efficient algorithm for doing LU factorization. And then we moved on to iterative methods. I introduced 3 variants, and we will see some more later on. One is the Jacobi iteration, and the other one is Gauss-Seidel, and then the SOR. And the key idea that we learned there is this notion of a fixed point iteration, and the convergence for any fixed point iteration is that the derivative of the function must be less than 1 in the case of a scalar equation. But in the case of a matrix case, we want the spectral radius, that is the largest eigenvalue, to be less than 1 for the iterative scheme to converge. So we're going to explore a little bit more about linear algebra today. And before I do that, I wanted to show you how these 2 ideas are combined, that is the direct method and the iterative method, to get solutions at a finite number of computations, but still get rid of the errors that you introduce in a direct method. So there are two problems in each, and we're trying to get rid of both the problems by combining the 2 effects. So a direct method will give you an inverse or a solution after a finite number of operations. It's called a direct method. You put a loop, and you know how many floating point operations are needed. Whereas in an iterative method, you are continuing to repeat a process of calculation until the error goes down below a certain value. And you don't know beforehand how many such iterations you need to do. So that's why that's a disadvantage. You don't know how many floating point operations you need. But the iterative methods have the advantage of getting rid of the errors, because to begin with, you introduce very large errors by making an arbitrary guess, and every successive scheme, successive iteration reduces that error towards 0. Okay? So if I have a direct method that has errors introduced by round-off errors, why can't I apply an iterative method on top of that to get rid of the round-off errors? Okay? So you also get to the final, that is, you get a very good initial guess for your iterative method by using the direct method. That's one way of looking at it. Okay? So here the idea is illustrated for just finding the inverse. So suppose you give me the matrix A, and I need to find its inverse B, which is error prone, okay, because I'm using one of the direct methods for finding the inverse. Okay, So what I'm going to do is I'm going to call B epsilon the error in B. So B has some errors, and there is an error associated with every element in B, and I'm going to call that as B epsilon. I don't know what it is. If I know that, of course, I can add it, and I get the correct inverse. Okay? So I don't know what B epsilon is. But what I know is if I take A and multiply it by B plus D epsilon, I will get the identity matrix. But if I take A and multiply it by B, I will get an approximate identity matrix. So the numbers may not be 111, maybe 0.994, 993, etc. Depends on to what extent the round-off error has corrupted the matrix B. Okay, so that is my starting point. Okay, and then what I'm going to do is devise an iterative scheme, a method that I apply repeatedly, so that I get better and better estimates of what actually B is. How do I do that? Okay, I just multiply AB, okay, and then AB epsilon. So I keep this on the left-hand side and move the A times B to the right-hand side. So I write it as I minus A minus B. So I've taken okay, this term and moved it to the right-hand side. Okay, and this term remains on the left-hand side. And then I do pre-multiply by B. Okay. So I pre-multiply this by B on both sides. Okay. So B and B here. Okay. So this becomes B times 1 minus AB, I minus AB. And on the left-hand side, I have B times A times B epsilon. Okay. And here I make an approximation. That approximation is B times A is I. Okay. Now I want you to think about why would that be a reasonable thing to do. On one side, I'm saying B times A is I. On the other side, I'm not saying, I'm not replacing it by I. If I replace it by I on the right hand side also, what do I get? I get 0. That means I get B epsilon as 0. That means there is no error, right? So there is some error in B, but when I multiply that A times B or B times A, that is left as a product without replacing it by identity matrix, but this one is replaced by an identity matrix. What would be the logic behind that?
The error is hopefully small enough.
There are errors in both places, but the error on the left-hand side appears as a multiplication factor. The error here is a subtraction, difference between two numbers of the same order of magnitude. Okay, so you cannot afford to ignore that in here, but you can replace it by an approximate identity matrix because it just multiplies it by a number that's close enough to I, close enough to 1. So it's not going to affect your calculations. Okay, using that idea, I have an estimate for B epsilon, the error. Okay, then what I'm doing is I'm adding B plus B epsilon. I'm adding B to both sides, and I'm going to call this as the next iterate, B at P plus 1. P plus 1 is the next iteration level. On the right hand side, I'm just going to combine these two, B plus B, which is 2BP. Okay, so 2I minus ABP. But these are done at the previous iteration level. So when P is equal to 0, this comes from direct method. So you do the direct method, you get an estimate of what B is, and put it on the right hand side, and what you get is an estimate for the next best guess. So it's like a fixed point iteration, and you repeat this process a certain number of times. And often you'll find a few times is good enough because the initial guess itself is pretty good for medium-sized matrices. The larger the size of the matrix, the more floating point operations, the more error-prone your initial guess will be coming from the direct method. Basically, it illustrates ideas of how I can combine the benefits of a direct method with an iterative method to develop an algorithm that does even better. Okay? Any questions on that?
Would you want to put like maybe a check before we go there to maybe look at the residual and see how big it is?
Right. The question is, I guess, for the benefit. Are you guys able to hear our discussion? The question was, even before you begin, do you want to test or check some measure of how error prone the answer is? And that is a good idea, right? So what might you do? You might take B times A, and you should get an identity matrix. So that means its determinant must be 1. So you might say, how close is the determinant to 1 of the resultant product, and develop a criterion based on that to say, okay, I'm going to go forward with an iterative scheme or not. Okay, that's a good idea. Any questions at the PI side? You guys are only receiving and you're not asking. The screen is not showing again. But it is being shared, it says here. Is it okay now? Okay, please do ask me from time to time if the screen goes blank. Every time it seems to have a different problem. So this happens when the network speed is not very high, I think. Stop sharing. So that should be network speed. Okay.
Maybe they just say that the lecture is not out.
No. I think they are used to it by now, right? You guys have the lecture notes downloaded from Moodle. So when you say you are not seeing the screen, you are not seeing what I am writing on the board, right? Yeah. Is it okay now? Are you able to see? Because it's showing here that your screen is being shared. No?
I think they need to have the lecture notes. Yeah, I don't know. I believe it's
Between the lecture notes and this screen, I will be switching. Okay, let me clarify. Yeah, I'm reading.
What are your sharing options?
The sharing options are to share the entire desktop, which would mean as I'm switching, the entire desktop is shared.
Is there a window on there?
There is a particular window that I could share that will cut down the load. That's what we need to try next. But the thing is, if I go to something else, they won't be seeing it.
It is.
Okay, when you switch from the board, we see the Adobe Connect screen. Yes. But when I switch back to the PDF annotator that has the notes on which I am writing, you are not able to see that? Oh, you see that as well? Okay. Okay, your friends are new to this. Maybe you can help them. Maybe you should get together in one room so that and have a higher speed connection in that room. One thing you will notice is when I switch between the Adobe screen and the PDF annotator screen, there may be a lag because the whole information has to be transmitted again. Okay, so I should probably give some time when I switch. So anybody else right now having the problem of not seeing the screen? My desktop, whatever is happening on my desktop?
One of us maybe to pull up to log into a computer.
I think you are logged in, right? You are able to see the.
Well, I'm not on the Adobe Connect.
If somebody can log in here, maybe we can monitor that as well.
What's the webpage for the? Is it on Google?
It is connect.
All right, yeah.
Dot.
They can see it.
Okay. You cannot. No. You cannot see me. Don't worry about seeing me because I have not enabled the video. You need to see only the screen, but you need to hear me. Okay. All right. So let's try to continue. Oh, the screen. Okay. Um,
It's working.
it came up. So how fast is it?
Yeah. Well, when you go back to that, it's almost immediate, but when you get to the Adobe annotator, it took about 5 seconds.
Okay.
3 seconds.
Are you guys in the same building? Maybe you can move into the room where it works with your friend, okay? But we need to work this out. Maybe on this Saturday I will set up a time with each one of you so that we can iron any further problems. I thought it was working till last lecture. You are in the same building, okay. All right. So that's the combination of direct and iterative method. Okay, the example of it. Now I'm going to move on to this eigenvalue, eigenvector problem that we talked about in the last class, and let's start with defining the dot product between two vectors. Okay, x1 and x2 are two vectors. What do we mean by the dot product? It's essentially the summation of all the elements, and it is also the same as the magnitude of x1, x2 times cos theta. Geometrically, we're talking about this as x1 and that as x2, and this is theta. The dot product is a scalar product, which essentially says you can think of it as x2 projected onto this, and then the product of that. Okay, and it's a useful measure for a number of reasons, and one of them is if the two vectors are perpendicular to each other, then theta is 90, cos theta is 0, and so you'll get the inner product, the dot product as 0. Okay, and this is an example of dot product between two unit vectors, I1 in the x1 direction, which has the components of 1 and 0, and I2 which has 0 and 1. So if I apply that definition onto this, I1 dot I2 will be 0. And that means they are perpendicular. This notion of perpendicularity is very important, not only for vectors but functions later on. And that would be abstract. What do we mean by saying two functions are perpendicular to each other, right? Here I can give you a geometrical picture. So we are going to go from this idea to the idea of linear independence. Okay? And that idea is easily transferable from vectors to functions. So what do I mean by linear independence? If you give me a set of vectors x1, x2, xn, okay, we say that they are linearly independent if the only way I can satisfy this equation, where I'm making a linear combination of every one of those vectors x1, x2, xn, by multiplying it with some number alpha 1, alpha 2, alpha n. Okay? The only way I can satisfy that equation is every alpha is 0. Okay? And that means all those vectors x1 to xn are linearly independent. I cannot express one as a linear combination of the others. Okay? And that is essential because if you want to construct any other vector, once you have a linearly independent set, you can use that as a basis to construct any other vector. What do I mean by that? Again, let's fall back on the simplest case. This is I1, that is I2. Okay? So I1 is 1, 0. I2 is 0, 1. Those are the two components of the vector. It's a two-dimensional space. So any vector that you want to construct in here, you can construct it as a linear combination of I1 and I2. You need to figure out what factor you need to put. So it may be alpha 1 I1 plus alpha 2 I2. I1 and I2 are basis vectors. They are known. You need to find out what alpha 1 and alpha 2 are, such that it represents that vector u. Okay? So any arbitrary vector can be represented as a linear combination of such a basis if they are linearly independent. The same idea will apply to functions. So we will talk about linearly independent set of functions, and then any arbitrary function can be expressed as a linear combination of those functions. That will prepare us for solving differential equations. Right now, we are preparing ourselves to solve algebraic equations. We have seen some efficient algorithms. Those are the ones that we will use in practice. So this is just to give you a conceptual idea of what eigenvectors are, and they are important in some of the stability problems that we will see later on. Okay? So that is a notion of what we mean by a linearly independent set of vectors that form a basis. So it's an introduction of that concept. Okay? The key idea is that you should not be able to express any one of the vectors given x1 in terms of all the other vectors. That is, you should not be able to find a non-trivial alpha 1, alpha 2, alpha n. They should all be 0. If you find, by mean non-trivial, non-zero values of alpha 1 and alpha 2, that means you are able to express one of the vectors as a linear combination of the others. Then they are linearly dependent. Okay? So how do we test for this idea? We have introduced a concept, and we have seen why we might need that. The next question is, how do I test for that? The test is fairly simple, because I can look at this equation that I have written here. This is actually a vector equation, because each component is a vector here. Okay? So x1 is a vector, x2 is a vector, and so 0 is a 0 vector on the right hand side. So I can write this as a vector matrix multiplication if I organize the first vector in this column. So x11, x21, x31. So the first index refers to the component of that vector x. The second index refers to the actual vector quantity. So here x2, for example, will be x12, x22, x32. So each column is packed with one of the vectors that you're given. So you're given n vectors, and I ask you to go and say, check whether it is linearly independent. Okay? So all you need to do is assemble all the vectors in columns like this to form a matrix. Okay? And then assemble alpha as a vector, which consists of alpha 1, alpha 2, alpha 3. Okay? And then you can write that particular equation in a vector matrix form as A times alpha equal to 0. You can figure that out, because you will have x11 times alpha 1 plus x12 times alpha 2 plus x13 times alpha 3. And that's what you will get when you expand this after you substitute. Okay? So there are actually n equations there on the component form. Okay? So we want all alpha to be equal to 0. So how can you satisfy this equation A alpha equal to 0? Either alpha is equal to 0 or A is equal to 0, right? So we want alpha to be equal to 0. We don't want A to be equal to 0. Okay? And that means that the determinant of A cannot be 0. Okay? If the determinant of A is not 0, it is not singular, then the only way that you can satisfy that equation is by setting alpha equal to 0. So the test for linear independence is formulate this matrix using the vectors along the columns, and then calculate the determinant of that. If the determinant comes out to be non-zero, those are linearly independent. Okay? So a fairly simple test. I'm moving slowly, and I will switch back to you guys there to ask how things are going. So are things all right there? Okay. So the Gram-Schmidt procedure, how many of you have not seen this? All of you have seen it. You have not seen that. Okay. So it's again a very simple idea and a simple algorithm based on that idea. What is the idea? The requirement is, if you are given a set of vectors, x1 to xn, set of vectors that are linearly independent. Okay, so you can test that. So you know that they are linearly independent, but they are not orthogonal. They are not perpendicular to each other. Okay. So how do I make that, from that, build an orthogonal set? Okay. So again, I can illustrate this by graphs in a two-dimensional case, but you need to understand that and then be able to extrapolate to a multi-dimensional case. Okay. So I give you two vectors, x1 and x2. So the way I've drawn it, it's obviously not perpendicular to each other. They're not orthogonal. Okay. So the very first step that we do is, then this is actually going to give you an orthonormal basis set, which means the vector length is going to be normalized to 1. So the first step that we do is, we can actually calculate the length of the vector. How do you calculate the length of the vector? Use some sort of a norm And here, for example, take the dot product of x1 with x1, take the square root, that is the length of the vector, and use that length of the vector to divide every element in x1 by that length. So u1 is the normalized vector. So u1 is pointing in the same direction as x1, but the length of u1 is equal to 1, whereas the length of x1 is not. We can calculate this according to that. Okay? So u1 may be going up to this arrow, okay? Whereas x1, the tip of the arrow, for example, is proportional to the length of the vector. Okay? So conceptually, it is very easy to understand. The very first step is, and we need to repeat this step for every vector. Okay? So for the two-dimensional case, the first step is simply normalize it. And the second step is, from this normalized vector, subtract a component of x2. Now x2 can be split into two directions. Okay? Let me try to venture into other columns. Okay? So x2 you can think of as being made up of two components. So you can decompose x2 in these two directions. Okay? So from x1, if I can subtract the component, that is component of x2 in the direction of x1, what I will be left with is only a component that is perpendicular to x1. Okay? So geometrically, are you following what is happening? You know u1, so along the direction of u1 from x2, I need to subtract. Okay? So I'm going to take x2, and from that I need to subtract u1. Okay? The component of x2 in the u1 direction. So c0 at this stage is an unknown number. I need to figure out what fraction of it I need to subtract. That means when I project onto this, I need to know what is this distance, okay, that I project. That's going to be u1, the u1 I have indicated up to this arrow point in red, multiplied by some number. I need to figure out what that number is. So I'm going to subtract exactly the component that will take out u1, and what I'll be left with is a component only perpendicular to it. Question?
Is CO the distance of x2's projection to the beginning of x1, or is it to the end of u1?
u1 is 1.
Right.
That is my new scale in which I will measure. Okay. So in the units of u1, I need to go a distance of c0. Okay. So c0 times u1 will be this projection all the way. Okay. Any other questions? Are you guys there following? I take it silence means good. Thank you. Okay. So that is the idea I need to implement. So I'm going to convert this into an algorithm. So the next step, as I say, u2 prime, that is a modified vector, is equal to the original vector x2, which is given to me, and the u1, which I just calculated in this step, multiplied by c0, which I don't know yet. I need to find out how much of from x2, how much of it I need to subtract in the u1 direction. And that is going to be perpendicular to x1. The u2 will be perpendicular to x1. So this is the process of orthogonalization. Okay? And how do I determine that c0? Well, I can take the dot product of this equation with respect to u1 transpose. Okay? So that's what I'm showing. u1 transpose multiplied by u2 dot. What is that? That's going to be 0, because we know that they're going to be perpendicular. Or another way of looking at it is, I must make that equal to 0 and then find what c0 is. Okay, I'm making them perpendicular. So I'm setting this equal to 0, and on the right hand side I will have u1 multiplied by dotted up with x2, and then minus c0 u1 dotted with u1, which will be 1, because it is a normalized vector. Okay, and that's why I essentially have 1. Okay, and that, yeah, question.
Why the transpose?
Because I want, well, it's a dot product, it's an inner product. So I'm looking at U1, all of them as column vectors.
Okay.
So I'm converting that column vector into a row vector.
No.
Okay. And the reason I switched to T here and not prime, sometimes in MATLAB the notation is prime. But here this U prime, U2 prime, I mean a modified vector. Okay, it's not transpose in that case. All are treated as column vectors. Okay. So from this equation, I have only one unknown, C naught. So C naught is equal to U1 transpose X2. So I found out what C1 is. So I can go back, substitute this C naught, and calculate this U1, U2 prime. What would be the next step? Normalize the U2 prime. So now you have U1 and U2 that are perpendicular to each other using X1 and X2. We use these two vectors to make them construct a vector that is normal. Now you need to do this in not in pictures anymore, unless you have very good 3D imagination, but take that concept and apply it. So U3 prime, the next vector that you're going to calculate, is going to be constructed from X3. Remember, each one of these vectors must be linearly independent. So X3 must contain a component that is not contained in X1 and X2. If X3 is linearly dependent on X1 and X2, what would happen? When you subtract components from X1 and X2, it will be 0. Right? Then we say that such a vector is forced to live in that two-dimensional space. You cannot represent it in a third-dimensional one. So they are linearly independent, so this will have a component that is perpendicular to both U1 and U2. So now I introduce two unknowns, C1 and C2. Okay, I need to find both of them. So I'm subtracting that from X3, I'm subtracting that component that is aligning with U1 direction, and I'm subtracting that component that is aligning in the U2 direction. Okay, so I need to find these two, means I need to have two conditions. But what are the two conditions? X3 is perpendicular to X1 or U1, and X3 is perpendicular to U2. So there are two conditions. So when I apply it for U1, U1 dot U3, I set that equal to 0. Okay, and on the right hand side, I will have U1 dot X3, which is this term, and U1 dot U1, which is 1. What about U1 dot U2? They're perpendicular to each other, right? So that term will give rise to a 0 here. Okay, so from that one, you can calculate simply C1 as U1 dot X3. Okay, and then take U3 and make it perpendicular to U2. So dot it, and this idea we are going to use later on in functions. Okay, when we talk about orthogonality of functions, how do we calculate these coefficients? We use that property. Okay, so it's important that you understand that. So on the left hand side, it is multiplied. Same equation. This equation is multiplied by U2, and we set that equal to 0. And on the right hand side, you will have U2 times X3, which is this term, and this will be 0. U1 times U2 will be 0 because U1 and U2 are perpendicular, and U2 dot U2 will be 1. So that gives rise to C2, from which you can calculate what C2 is. So I'm actually replacing C1 and C2 in that original formula that we wrote here. Okay, so this becomes the algorithm for finding the next vector. Now you can get the pattern, right? So all you need to do is, after you've done it for a few times, you can write a general algorithm. So there are two steps. Normalize it, and then subtract all the components from the previous normalized subset of vectors to construct the next one that is perpendicular to all the others. So do this from 2 to n. And there is a MATLAB function implementing this, and built-in one as well, and the one that I have written. The built-in one is called R. Okay? And so you pack all your vectors in a matrix A and pass it, and you'll return the vectors in a matrix called Q, and those will all be, every column will be perpendicular to everything else. Obviously, any built-in MATLAB function is going to be much, much more sophisticated than what we can write. Okay, so we are exploring the ideas, showing you how to implement it, and then showing that there is much more powerful algorithm in MATLAB. Let me just ask those guys a question. How many of you are new to MATLAB? Can each one of you answer that question for me? Because I do expect you to the first assignment to have some level of familiarity with MATLAB. Is there anybody who has not used MATLAB before? Okay, so there is on YouTube channel, there is a course that I gave last term to undergraduates just on MATLAB, about 10 lectures or so. So if you have not used it, probably you need to look at that and then communicate with me. Okay, so if you have used it in the past, it should not be very difficult. It's fairly easy to pick it up. So, okay, there are 3 of you at least that have used, 1 person who hasn't used. So here also the same thing applies. If you have not used MATLAB, you need additional help, you need to let me know. Okay, MATLAB is a good environment to explore all these easy to implement ideas. All right. Eigenvalue problem. There are 2 very good references. One by Wilkinson, which is a more classic old reference, the algebraic eigenvalue problem, and a more recent one by Yusuf Saad, numerical methods for large eigenvalue problems. So we are going to actually develop some very simple ideas using something called power iteration to solve the eigenvalue problem. What is the eigenvalue problem? Given a matrix A, you need to find a set of vectors which, when operated on A, give you the same vector except for a scaling. Okay, so if they satisfy this property, then we call these vectors as the eigenvectors and lambda as the eigenvalues corresponding to those. Okay, so you can simply take this to the left-hand side and rearrange that equation as A minus lambda I times x equal to 0. Okay, so once again, if you want a trivial solution for x, one way of satisfying this is that x equal to 0. That will satisfy that. But we don't want that. We want a non-trivial set of vectors. So if you have n equations, n by n system, you will have n such vectors. Okay, and we are going to consider cases where there are no degeneracies, just exploring the ideas. But the book by Wilkinson talks about all kinds of degeneracies. What do I mean by degeneracies? What happens if an eigenvalue occurs with a multiplicity of 2 or 3, okay, repeated eigenvalues. So there are specialized algorithms that we need to extend, but for initial purposes of discussion, let's assume that all the eigenvalues are distinct. Okay, so then there will be n distinct eigenvalues, and there will be n sets of eigenvectors that satisfy that equation. The way that we get at that is, because we want x to be non-trivial, we force the determinant of a minus lambda I to be equal to 0. Okay, so if that is 0, then if this is 0, then x need not be 0. That will give you the non-zero eigenvectors. So as I said, for an n by n system, there will be n such eigenvalues. And determinant we know how to expand, and MATLAB has nice tools for, if you pass a matrix A to a function called poly, it will actually do the expansion and give you the characteristic polynomial. Okay, you will end up with a polynomial of degree n in lambda, and you can solve for all the roots of that. Those will be your eigenvalues. And once you get the eigenvalues, you take them, put it back in here, and solve for the eigenvector. Now, eigenvectors are not uniquely determined. Only the direction is determined. The magnitude is arbitrary. Okay, so what would happen is, when you put back the eigenvalue here, you will notice that you will have n equations, but they will be linearly dependent. So you fix one of the components of x1 as arbitrary number, and you can solve for the remaining n minus 1 by n minus 1 matrix. Okay. Now, if something that I'm saying is not making sense, please do stop and ask. Okay. So that is the way to conceptually understand what eigenvectors are, and what eigenvalues are. Something that satisfies this equation, and the MATLAB built-in function that you will use is EIG, and pass the matrix operator A and it returned two answers. One would be a matrix containing eigenvectors. This will contain eigenvectors. And B will contain the eigenvalues. Okay? So V will contain columns of numbers, and each column is one eigenvector. Okay? And D will be a diagonal matrix, and on the diagonal elements you will have the corresponding eigenvalues. Any questions? Yeah.
The answer, the vectors and the values are correlated to the output, correct? As in the first eigenvector corresponds to the first eigenvalue.
Right,
That output,
right, yeah. The ordering is kind of arbitrary. So you will find, for example, if you find the eigenvalues from the matrix D in a certain order, those will correspond with the corresponding eigenvectors in the column position. But if you do poly A, that will also give you the characteristic polynomial, which you can pass to roots, which will give you the eigenvalues too, but it will be in a different order. Because all you're doing is you're finding one root to that equation, and then we'll talk about a deflation technique, which will make your iterative scheme go away from that and find the next eigenvalue, the next eigenvalue. So the order in which these are found may be different. Okay. So here is an example, a 3x3 example, in how you would implement it in MATLAB. So you define your matrix in MATLAB like this: 2, 4, 3, semicolon 4, 4, 3 for the next column, next row, semicolon 3, 3, 5. Okay, and it echoes what the entry is, and then you pass it to EIG, and it returns these two. Okay, so your question is, this eigenvalue will correspond to that eigenvector, okay, and this one will correspond to that one. Now, if you take these eigenvalues, the set of eigenvectors forms a natural basis set. Okay, they are linearly independent, and they are also orthogonal if this matrix is symmetric. If it is not symmetric, then they have something called a bi-orthogonality property that we will see what it is. Okay? But suppose it is symmetric. In this particular case, it is not. But if you started off with a symmetric matrix, you will get these three columns. Okay? So if you take the inner product of the first column with the second column, it will be 0. First with the third, it will be 0. First with the first itself will be 1. One of the things that I'm asking you to explore in your assignment is these orthogonality issues after you find out for a 5x5 or a 6x6 tridiagonal matrix, symmetric and non-symmetric cases. Okay, so here the same matrix is passed to a function called poly, and that returns the roots of the characteristic polynomial. Okay, so the C will contain the coefficients of the polynomial, and you take those coefficients and pass it to the roots function. Roots function takes any polynomial and finds the roots of the polynomial. Whereas this is the function that is key, which takes any matrix and converts that into its characteristic polynomial. It is the process of building the determinant of A minus lambda I. And as I said, the order may not be same, so maybe let's check that. It is reversed, right? Okay, so so the C1, C2 are given in this particular order. When poly returns the coefficients of the polynomial, C1 is the one that goes with lambda to the power n. C2 is the one that goes with lambda to the power n minus 1, etc. So for an nth degree polynomial, you will have n plus 1 coefficients. So in our case, we had a third degree polynomial, so we have these 4 coefficients. Okay? So this goes with lambda cubed, lambda squared, lambda, and the constant. Now, as I said, if the matrix A is symmetric, the set of eigenvectors are linearly independent and orthogonal. So they form a basis, which gives us an idea that I can go back and in solving Ax equal to B, I can construct the solution using these eigenvectors. Because x is an arbitrary vector in that space, so if I have these eigenvectors, I can construct that solution, and I will show you that later on. But what happens if A is not symmetric? Okay? Then if I multiply that matrix from the left side, what I did previously was Ax equals lambda x. So I multiplied that A from the right hand side, and I said that is equal to lambda x. So if I multiply it from the left hand side, y, here I'm using the prime as a transpose. Okay? So y prime times A equals y prime lambda. This is called a left eigenvector. The eigenvalues are the same. Okay? So you can once again move this to the left hand side and combine it as y transpose times A minus lambda I. Again, we don't want the y transpose to be trivial, so we make the determinant of this equal to 0. So the eigenvalues are the same. It's the same set of eigenvalues from the same problem, the same equation. But there is one eigenvector that you can calculate by operating from the right. There is another eigenvector that you can calculate by operating from the left. Will these two be the same? They will be the same if A is symmetric. Okay? But if A is not symmetric, then the left and right eigenvectors are quite distinct. Okay? They are distinct. They are different. And they are bi-orthogonal. What that means is, if you take one vector from the set Y, okay, you will have vector y1, y2, yn. So n set of vectors on the left side and n set of vectors on the right side. So if you take one of them from the left side and multiply it with, for the same corresponding eigenvalue, okay, with the set from the right, those will be kind of pointing in the same direction. But if you take any other eigenvector from the right, they will all be perpendicular to the eigenvector from the left. That's what we mean by bi-orthogonal. Okay? So every set from the left, I didn't realize that it acts even I didn't touch it. Okay? So every set on the left is perpendicular to every set on the right. Okay? That we call bi-orthogonal system. Questions?
Yeah.
Yeah?
So the differences between corresponding left and right eigenvectors which come from the same eigenvalue is some kind of scalar multiple?
No, it's not a scalar multiple. It's not a scalar multiple. It's obtained by different operation. This is obtained by multiplying the vector from the right side of A. This is multiplied by multiplying A by from the left side, the vector left side. Okay. So what it means, we have to look at geometrically.
Yes.
Suppose I have two vectors, x1. That's an eigenvector. Okay. And I have a 2 by 2 problem. So this is another eigenvector. I deliberately drawn it such that they are not orthogonal. Okay. If the matrix A is not symmetric, x1 and x2 will be linearly independent, but they are not required to be orthogonal. Okay. But for the same matrix, I can also calculate another set of vectors, and I'm going to call them as y1 and y2. They are I have a recipe for calculating them. I'm calculating them by this equation. Okay. So y1 and y2 are also not orthogonal, but they are linearly independent. What this bi-orthogonality says is that x1 is perpendicular to y1. Sorry, x1 is perpendicular to y2. I messed it up there. Let me do it again. x1 is perpendicular to y, but I think you get the idea already, right?
X1 is perpendicular to y1.
x1 is perpendicular to y2.
y2.
We will show why that is. Mathematically, we will show. I'm just stating a fact that every vector from the set Y is perpendicular to every other vector that comes from different eigenvalues. Y1 and x1 come from the same eigenvalue. Remember, the eigenvalue set is the same. That's what I said.
I misunderstood. I thought it was
So you have the operator A, the matrix A, you solve this problem, you get a set of eigenvalues, and that equation is the same whether you operate from the left or the right. It's just a determinant of that. So you have n eigenvalues. For each eigenvalue, when you put it back into this equation, you're going to get an eigenvector. We'll get n eigenvectors for x, n eigenvectors for y. Okay, and what we are saying is x1 will be perpendicular to y2, and similarly x2 will be perpendicular to y1.
Would in a higher order system, x1 would be perpendicular to
y2, y3,
and y3,
yeah,
and y4.
exactly,
Ah.
exactly, right, yeah. Are there any questions from there at the PI? Silence means I will take it. All right, thank you. Okay, so how do I show that these are biorthogonal? I just made a statement that these are biorthogonal, introduced the idea geometrically to think about what biorthogonality is, but how do we show that? It's not very difficult, it's just a few lines to demonstrate that. So I start with the equation AX equals, write it, and then I'll show you how this comes, okay? So AX equals lambda x, but I'm going to put some indices there. Okay? So lambda I, xi. So when I am using, I have n set of vectors. When I'm using one vector, that goes with one eigenvalue. That's my starting point. I pre-multiply this by y transpose with a different vector j. Okay? You understand, sir? So this comes to this when I pre-multiply this by a set from the left eigenvector, but corresponding to a different eigenvalue, lambda j. Okay? Then I do the same thing for the second equation, where I start with y j transpose A equals lambda j yj transpose. And I right multiply this by xi. Okay. So the first equation I have multiplied the left multiplication and the second one right multiplication, but I and j are different eigenvalues. Okay. Now what I made is I made the left hand side in both the cases the same. What would be the left hand side? Will it be a vector, a matrix, a scalar? It would be a scalar, right? Because A times x will be a vector, okay, and I multiply, it's an inner product, the transpose, okay, so that will be a scalar. So I'm calculating the scalar two different ways, but they're going to be the same scalar. So if I subtract one from the other, okay, 1 and 2, and I write say 1 minus 2 or 2 minus 1. So the left hand side is going to be 0, on the right hand side I will have lambda I minus lambda j multiplied by yj transpose dot xi. So that is the inner product between the left eigenvector and the right eigenvector for two different eigenvalues. Okay, and I want that to be equal to 0, but I've said that these eigenvalues are distinct, so that cannot be 0. This proof has to be modified if you have multiplicity now, right? But if you don't have multiplicity, if all the eigenvalues are distinct, this cannot be 0. So yj times xi must be 0. That shows that these two are orthogonal. For any two distinct set of eigenvalues, we take a set from the left and a set from the right, and they are perpendicular to each other. Now, we know that MATLAB has a built-in function called EIG, which gives us the eigenvalues and the eigenvectors. It's a great tool for learning. Even if you have 20 by 20, 100 by 100, it still is fast enough. The processes are fast enough. But if you have 10,000 by 10,000 matrix, you can bring MATLAB to its knees. It will do the calculations. If you pass a 10,000 by 10,000 matrix to MATLAB, ask it to calculate all the 10,000 eigenvalues, eigenvectors, it may take months. Okay, so we need efficient ways of calculating the eigenvalues, and often we don't need all the eigenvalues. We need eigenvalues that are the largest or the smallest. What was the case that we already saw where we need the largest eigenvalue? In the iteration scheme, Gauss, Seidel, etc. We wanted the spectral radius to be less than 1. So we want the largest eigenvalue to be less than 1. So is there a way to calculate only the largest eigenvalue, or only the smallest eigenvalue, or only the eigenvalue close to some region? Okay, eigenvalue closest to 2, eigenvalue closest to 5. So we need to develop some schemes, and one of them is called the power iteration. Idea is extremely simple, and I don't know how anybody came up with this, but we need to understand why it works. I'll explain what it is, and then we'll explore why it works. So you give me the matrix A, and you ask me the task of finding the eigenvalue and the eigenvector corresponding to the largest eigenvalue. Okay, so I come up with some initial vector z0, some random vector that I pick. Okay, and I multiply that by A. Okay, and I call that as a new vector p plus 1. So I'm setting up an iterative scheme. P goes from 0, 1, indefinite number of times. But I take a vector multiplied by A, get a new vector, and I scale that vector, because if I keep doing this, I might get numbers that are, because I keep multiplying it, I get numbers that are bigger and bigger and bigger. Okay, so, and I'm interested only in finding the direction of the vector. Eigenvectors are known only to the direction, right? So I can always normalize it. So the second step is nothing but scaling that vector. So I get a yp plus 1, and for example, I divide that by kp plus 1. K is some number, the largest number in y. I can take the largest number in the vector y, divided by that, and I call the new vector as z plus 1. Okay, so this is just a scale factor. And I take the z plus 1, put it on the right hand side. So I increment the index, and I get a new y, and I scale it, and I repeat this process. What happens? If somebody asked me when I was a graduate student, I wouldn't know. Right? But what happens is that that vector that you started off with an arbitrary thing goes towards the largest eigenvector corresponding to the largest eigenvalue. Okay? Why does that happen? Okay? And if we understand why does that happen, then we can ask, how can I modify this to get the smallest eigenvalue or eigenvalue closest to some specific value that I'm interested in? Any questions on this? Do you understand what we are doing? Start with some arbitrary vector, keep multiplying it by A, produce a new vector, scale that vector, and keep repeating it. And if you repeat it 10, 20 times, you will find that this arbitrary vector aligns itself with that eigenvector corresponding to the largest eigenvalue. There are others. How do we get them? That's a separate issue. Okay, but this simple iterative process gives you a way of getting at the largest eigenvalue and its vector. Why does it work? So this is an important idea. This idea reappears in many times in control, process control, etc. What is the idea there? The idea is I started off with an arbitrary vector. Okay? That arbitrary vector can be represented as a linear combination of basis vectors. In this case, the basis vectors are the eigenvectors. Okay? So, but alpha I is an unknown. I need to find out what alpha I is. That is, how much of vector 1 should be blended with how much of vector 2 and vector 3, etc. So when I blend all of them correctly, I get the actual vector that I started off with. So one of the requirements is that this vector must be truly arbitrary, meaning it should have components spanning the entire space. Okay, what does that mean? Suppose I have, this is a crude attempt to draw a 3D situation, x1, x2, x3. Okay, so these are the three eigenvectors. Okay, so I have three-dimensional space, and I want z naught that contains components in the x1 direction, in the x2 direction, and in the x3 direction. If I pick z naught that lies only in this plane, x1, x3, doesn't have any component on the x2. Okay, then I will get into difficulty because the coefficient multiplying x2 here will be 0. Okay, so that kind of an initial guess may constrain it to find the eigenvector that lives in that subspace. So between x1 and x3, whichever is the larger, it will probably go to that. But it will not go to the true largest eigenvalue because you have not sampled the entire space. So in that sense, Z0 must be truly random, spanning the entire space that you are interested in. Okay, so this is important to understand. What we are saying here is that arbitrary vector can be constructed as a linear combination of your basis set. The basis set is the eigenvectors in this case. Okay, and what are we doing in our iterative scheme? We are multiplying A by Z0. Okay, so here that's it. Okay, so y1 is equal to A times Z0 when P is equal to 0. Okay, but Z0 has this representation that we just wrote down. So Z0 is the same as summation of alpha I x. So I'm going to multiply this by A, every one of the term by A. Okay, but xi's are the basis vectors or the eigenvectors. So what is A times x? The same as lambda times x, lambda I times x. Okay, so this y1 has a representation. We are not doing any of these operations. We are trying to understand why it works. The operation that you do is simply those two lines. Okay, multiply, scale, and repeat that. But that is equivalent to the expression that we see here, alpha I lambda I xi. Okay, that is for 1, the first iterator. And then we are going to scale it, right? So y2, when p is equal to 2, or is p equal to 1, y2 will be A Z1. And that will be A1 over K1. K1 is the scale factor multiplied by y1. Y1 we already have. So take that y1 and substitute in here. So you will get a 1 over K1 factor plus a summation of alpha I lambda I. Y1 is replaced by xi, but it is multiplied by pre-multiplied by A. So you get 1 more A xi. You replace that by 1 more lambda xi, so this becomes lambda squared. So every time you multiply by the vector, the power of these eigen, and these are actually all the eigenvalues, summation over the entire space, okay? They go up one by one. Do you follow the development so far? Okay? So if you keep repeating it at yp plus 1, okay, you will get the product of all the scale factors in the denominator. Those are just numbers to keep the overall calculation magnitude reasonable. But the key is you will get this lambda I to the power p plus 1. Okay, and the basis vectors will be xi remain as such, summation over all the vectors. So what I'm going to do is divide by the largest eigenvalue lambda 1. So I'm dividing by lambda 1 to the power p plus 1, and I'm multiplying by lambda 1 to the power p plus 1. Okay. Now you can start to interpret what is happening. What would be the ratio? Now here I have a summation of n terms. Okay, but what happens in reality is this arbitrary vector aligns itself with x1, the eigenvector corresponding to the largest eigenvalue. You can understand why that is from interpreting this equation. What would happen to lambda I over lambda 1? If lambda 1 is the largest eigenvalue, what would be lambda 2 over lambda 1? Less than 1. Lambda 3 over lambda 1 will be less than 1. Lambda 1 and lambda 1 would be the only one that is 1. So if you raise a number that is 1 to the power p plus 1, that's going to remain as 1. But all the other numbers will become progressively smaller and smaller. Right? So from the summation, what is going to happen is with every iteration, all the other terms will get progressively smaller and smaller. That is, the eigenvector x2 will be multiplied by a small number, x3 will be multiplied by a small number. So they don't make as much contribution to this vector y. So y contains mostly components of x1. So y aligns itself with x1. Okay? So all these are just scale factors. Again, this explanation will break if there are two eigenvalues that are close to each other, that are the largest. What do you think will happen then? If I have a matrix which has two eigenvalues that are the largest but the same magnitude, you can understand it by simply going through the same logic. Okay, now you will have lambda 1 over lambda 1, lambda 2 over lambda 1, both will be of order 1. Okay, so the vector that you're going to get here is going to be a linear combination of those two eigenvectors, x1 and x2. So it will live in that subspace of x1 and x2. You won't be able to figure out which is x1 and which is x2. Okay? Any questions? Okay, so this tells us why the power iteration works. Okay, and later on, when we look at dynamical systems, we would want to calculate the largest eigenvalue and make sure that it is within the unit circle. Okay, we will relate that to stability, and at that time, we will find usefulness for this. This idea has been generalized. Yeah, question. Sorry.
You still don't need to know the largest eigenvalue a priori, right?
Good question. I was hoping that somebody will ask that. The question is, after I do this, I know only the eigenvector. How do I get the eigenvalue? That's what you're asking, right?
No, I'm saying this is just the proof that this algorithm will work. But
Right.
you still don't need to know that. You still don't need to know the largest eigenvalue before you start this.
Right, right. So you don't. The question is, you don't need to know what the largest eigenvalue is. If you, this is an explanation of why it works, but the scheme itself consists of only these two lines. So given a, start with some random vector, keep repeating it, scaling it, you will get the eigenvector, and that will correspond to the largest eigenvalue. Okay, so you don't need to know what that value is a priori.
There is a way to kind of know if one exists and what it might be. If you Google or look up the Gershgorn circle theorem, that kind of gives you a nice geometric picture. You look at the row sums and the column sums, and it tells you it has to be bounded with a disk that lives.
Yeah, the Gershgorn theorem gives you a bound on the eigenvalues, and they have been used a lot in particularly control theory. Control theory also, process control, those who are in that area, it's very important to know where the eigenvalues are and to control them. You want them in the left half plane for stability. If you develop a feedback design and you're moving the eigenvalues to the right hand side, you're going to have an unstable system, right? So, and hydrodynamic stability theory is all about finding these eigenvalues where they are and not necessarily controlling them, but at least knowing why a particular flow is unstable. Okay. The variation on that question would be, okay, if I apply this procedure, I'm going to get a vector, and that vector is going to be pointing in the direction of the largest eigenvalue. Eigenvector. How do I get the eigenvalue itself? There is something called a Rayleigh quotient, which will allow you to calculate that, and that is simply coming from this equation: Ax equals lambda x. Let's put 1. So the first eigenvector and the corresponding eigenvalue. So we know A, and through this iterative process, we have figured out what x1 is, the direction of the eigenvector. So the only unknown there is lambda. Okay. So how do you estimate lambda? Because this is still a vector equation, right? Also, so lambda will be given by x1 transpose A x1, and that would be a scalar number. Okay, because Ax will be a vector, and you're multiplying it by a row vector x transpose divided by x1 transpose x1. That will also be a scalar. Okay, so once you find the direction of the largest eigenvector, you plug it into this, and you get lambda. That is an estimate of the eigenvalue.
Why you divide by?
All you're doing is rearranging it. I should write this because I'm pre-multiplying both sides by x1 transpose x1. See, I started off with Ax1. Some part of the boards are not. Lambda 1 x1. I started off with this. I pre-multiply both by x1 transpose, and then I move that x1 transpose x1 to the denominator.
I'm getting transposes and inverses confused. So it's like that should be.
No, transpose changing rows and columns. Yeah.
Next question. The K multiplication seems arbitrary.
It is arbitrary, and your purpose there is to keep the length of the vector bounded. That it's only the direction of the eigenvector that matters. The actual length doesn't matter. So if you take a number and keep multiplying it by a matrix, suppose the matrix has a property that it amplifies the length of the vector every time, then the length of the vector is going to go to infinity if you keep repeating that.
Okay.
So all you are saying is, okay, I'm going to shrink the vector again.
Okay.
Okay. So the simplest way to do that would be, after you produce yp plus 1, scan, pick the largest number in that vector, divide by it.
Okay.
Nothing.
Yeah, K is actually the norm of the vector. I think that K is actually the norm of the vector.
You can use the norm, yeah. Some of the other features also become evident from the above analysis. One is the convergence rate will be faster if the largest eigenvalue is well separated from the remaining values. Does that make sense to you, what I mean by that? If lambda 1 over lambda 1 is 1, and the next eigenvalue lambda 2 over lambda 1, if it is 0.999, okay, that ratio, then the convergence rate will be very slow because you have two eigenvectors that are very close to each other. Whereas if lambda 2 is much smaller than lambda 1, so that lambda 2 over lambda 1 is 0.3, then you just exponentiate it 4 times, 5 times, you're going to drive it to 0. Okay? That's what we are saying. So the convergence rate will be fast if the eigenvalues are well separated from each other, from the remaining ones. Okay? So if the largest eigenvalue occurs with the multiplicity of 2, then the above sequence will not converge. But what will happen is the vector will live in the subspace of x1 and x2. So you will find it hard to detect whether it has converged. How do you detect it has converged? The direction should not change, right? But if the vector keeps oscillating between two values from iteration to iteration, you will never converge. Okay? So if it fails to converge in your test for convergence, you can suspect that you are in a subspace of your eigenvector space. The other thing is, again we talked about this, if the initial guess does not contain any component in the direction of x1, then the sequence will converge to the next largest eigenvalue. That's an important observation. So what we are saying is, don't pick z0 strictly arbitrarily. If you pick it arbitrarily, it's going to contain all components. It's going to go to the largest one. So having found the largest one, suppose I say I want to find the next largest one. What do I do? I know already what the largest one is. So pick an arbitrary vector, subtract that component that you already know. We know how to do that. Gram-Schmidt, we've done that, right? So if you subtract that, then use that as your initial guess. Okay? And hope that the round of errors don't introduce something that will ask to go back to the full space. Okay? Then you will be able to get the next largest eigenvalue. So here is the power iteration implementation in MATLAB. Okay? So initially I am giving you a lot of this code because you may not be familiar with MATLAB. Those who are not familiar, try to understand, read this, understand this, run it, play with it with a few examples. And the first assignment is meant to do exactly that. Okay? So implementation of some of these algorithms. Inverse iteration. So maybe we will stop there. We're almost out of time and continue the next class. Okay, any questions from PI guys? Yeah, I have not set up a link for submission yet on Moodle. Within the next half an hour when I go back to my office, I will set up the link and then send you an email. It's due by next Wednesday by 4 o'clock. Okay, so you will have a place where you can click and it will ask you to upload a particular file, a single file. So if you have the results in many files, then zip them up and okay, thank you. See you on next Monday.